This is Sleepy Space, a slow space story to help you fall asleep. When you look up at the night sky on a clear evening, the stars seem close. They appear as gentle points of light, scattered across the darkness like dust on a velvet. It can feel as though they are almost within reach, as if you could stretch out your hand and brush your fingers across them. This feeling is ancient, and it is wrong. For most of human history, we believed the stars were exactly what they appeared to be. Small lights affixed to a dome above the earth. Lanterns hung in the heavens. Objects no farther away than the moon, perhaps embedded in crystal spheres that turned slowly overhead. The universe felt intimate, enclosed, manageable, but the stars are not close. They are not small. And the distance separating us from even the nearest among them belongs to a scale that resists human thought. The closest star system to our own sun is Alpha Centauri. It lies 4.37 light-years away. That phrase sounds harmless. 4.37 light-years. It feels almost nearby, especially when spoken aloud. But the number hides its meaning. A light-year is not a unit of time. It is a unit of distance, the distance light travels in 1 year. Light is the fastest thing in the universe. Nothing outruns it. It crosses the distance from Earth to the Moon in just over 1 second. It takes a little more than 8 minutes to travel from the Sun to Earth, a distance of about 150 million kilometers. That span from our star to our planet defines what astronomers call one astronomical unit. It is the ruler we use to measure the solar system. A light year is not one astronomical unit. It is not 1,000. It is nearly 63,000 astronomical units. 1 light year is roughly 9.5 trillion kilometers. 9 followed by 12 zeros. A number so large it dissolves the moment you try to imagine it. So let us try to shrink it. Imagine walking to Alpha Centauri. You walk at a steady pace, 5 kilometers every hour without ever stopping. No sleep, no rest, no hesitation. At that speed, the journey would take more than 200 million years. You would need to walk longer than dinosaurs have been extinct. Walking feels unfair, so let us drive instead. Suppose you enter a car and travel at 100 kilometers per hour, never slowing down, never refueling, never turning back. The journey would still take more than 40 million years. Entire species would rise and vanish while you kept your hands on the wheel. Perhaps flight will help. A commercial airliner cruising at 900 kilometers per hour would require nearly 5 million years to reach Alpha Centauri. In that time, continents would shift, mountains would erode, the night sky itself would change. Even our fastest machines fail. Voyager 1, launched in 1977, is the most distant human-made object in existence. It travels faster than anything humanity has ever built, roughly 17 kilometers per second. It has already left the solar system, passing beyond the influence of the sun's wind and into interstellar space. And yet, even Voyager 1 would need more than 70,000 years to reach Alpha Centauri, if it were aimed in that direction, which it is not. This is the reality of interstellar space. The stars are not neighbors. They are islands separated by oceans so vast that even our fastest ships drift like leaves. When you look at the stars tonight, you are not seeing them as they are now. You are seeing them as they were. The light entering your eyes left those distant suns years ago, decades ago, centuries ago. The light from Alpha Centauri began its journey more than 4 years in the past. If Alpha Centauri vanished tomorrow, we would not know for another 4 years. We would continue to see it shining faithfully in the sky, long after it was gone. The stars appear close because our eyes cannot perceive depth across such distances. Everything is projected onto the same dark canvas. Every star looks equidistant, as though they are painted on the inside of a vast sphere. This illusion shaped human thought for millennia. We once believed the universe was small, cozy, within reach. It is not. The universe is almost entirely empty, and the stars, for all their brightness, are impossibly far away. Alpha Centauri is our nearest neighbor, the closest other sun we will ever know without leaving home, and even it is unreachable by any technology we currently possess. This is not a temporary limitation. It is not a problem waiting for better engines or clever engineering. The distance itself is the barrier. And yet, despite this, we have measured it. We know exactly how far Alpha Centauri lies. We have charted its motion, analyzed its light, and discovered planets orbiting its stars. From a single small world, orbiting an unremarkable star, we have mapped the abyss. To truly understand what these distances mean, we must begin closer. Before the gulf between stars, before the emptiness of interstellar space, we must first understand the space we already inhabit, the region around our own sun. Only then can we begin to comprehend the scale of the universe beyond it. The sun is vast. It contains more than 99% of all the mass in our solar system. Every planet, every moon, every asteroid and comet combined makes up less than 1% of what remains. The sun is not simply the center of our world. It is, for all practical purposes, the only thing that matters when you add up the numbers. It is also extraordinarily far away. We do not think of it that way, perhaps because we see it every day, because its light reaches us so reliably. But the sun sits at an average distance of about 150 million kilometers from Earth. This distance has a name. Astronomers call it 1 astronomical unit. It is our measuring stick, the baseline against which we compare every other distance in space. 150 million kilometers is not an easy distance to visualize. Light, which travels faster than anything else we know, takes 8 minutes and 20 seconds to cross it. When you step outside in the morning and feel the sun's warmth on your face, you are feeling light that left the sun's surface more than 8 minutes ago. You are experiencing the past. If the sun were to suddenly vanish, we would not notice for 8 minutes. The sky would remain bright. The world would continue as though nothing had changed. And then, all at once, it would go dark. A spacecraft traveling to the sun would take far longer. The Parker Solar Probe, one of the fastest objects humanity has ever launched, takes months to reach the sun's outer atmosphere, even with multiple gravitational assists from Venus. For a conventional spacecraft traveling in a straight line, the journey might take half a year or more. This distance, this 1 astronomical unit, is the foundation of how we measure the stars. To understand stellar distances, astronomers do not rely on sending probes or bouncing signals. Instead, they use the Earth's orbit itself as a tool. They use the fact that our planet moves. The technique is called parallax. You have experienced it many times without realizing it. Hold your thumb up in front of your face and close one eye. Note where your thumb appears against the background. Now switch eyes. Your thumb seems to shift position, even though it has not moved. This apparent shift happens because you are viewing your thumb from two slightly different positions: the position of your left eye and the position of your right eye. Astronomers do the same thing with stars, but instead of using two eyes, they use two positions of the Earth in its orbit. They observe a nearby star in January, when the Earth is on one side of the Sun. Then they observe it again in July, when the Earth has traveled to the opposite side of its orbit. The total distance between these two observation points is twice the distance from the Earth to the Sun. 2 astronomical units, or about 300 million kilometers. From these two vantage points, separated by half a year and 300 million kilometers, nearby stars appear to shift their position very slightly against the distant background stars. This shift is called the parallax angle. It is incredibly small. Even for the nearest stars, the shift is less than 1 arcsecond. An arcsecond is 1/3600th of a single degree. If you divided a full circle into more than 1 million equal slices, each slice would be about 1 arcsecond wide. The smaller the parallax angle, the farther away the star. A star that shifts by 1 arcsecond over the course of 6 months lies at a distance astronomers call 1 parsec. The word parsec is shorthand for parallax arcsecond. It represents the distance at which a star would have a parallax of exactly 1 arcsecond when viewed from opposite sides of Earth's orbit. 1 parsec equals about 3.26 light years, or roughly 200,000 astronomical units, or roughly 30 trillion kilometers. This might seem like an arbitrary unit, but it arises naturally from the geometry of how we measure stars. It is the distance that corresponds directly to the angles we observe. For astronomers, parsecs are often more useful than light years because they connect immediately to the measurements taken through telescopes. Alpha Centauri, the closest star system to our Sun, has a parallax of about 3/4 of an arcsecond. This places it at a distance of roughly 1.3 parsecs, or 4.37 light years. The measurement is astonishingly precise, considering the angles involved are so small that no human eye could ever perceive them. We needed telescopes, careful observations, and mathematics to reveal what our senses alone could never detect. Before parallax measurements became possible, we did not know how far away the stars were. We knew they were distant, but we had no numbers, no scale. We could only guess. The first successful parallax measurement of a star occurred in the 1830s, when Friedrich Bessel measured the distance to a star called 61 Cygni. It was a triumph of precision and patience. For the first time, humanity knew the true scale of the space beyond the solar system. That scale was staggering. Even the nearest stars were thousands of times farther than the outer planets. The solar system, which had seemed so vast, was revealed to be a tiny island. The distances to the stars were of an entirely different order, a different realm of existence. We now use parallax to measure thousands of stars. Space telescopes like Gaia have mapped more than 1 billion stars with extraordinary precision, measuring parallaxes far smaller than Bessel could have imagined. We have extended our vision outward, charting the positions and distances of stars across thousands of light years. But the principle remains the same. We are still using the Earth's orbit, the the same 1 astronomical unit radius as our cosmic measuring tape. The Sun anchors us. Its distance defines our unit of measurement. Its gravity keeps us moving in the circle we need to measure the stars. Everything we know about the distances to other suns begins here, with our own star and the space between us and its light. Now, with our tools understood and our baseline established, we can turn our attention outward to the nearest of those distant suns. Alpha Centauri is not a single star. It is a system of 3 stars, bound together by gravity, orbiting a common center of mass. From Earth, these 3 stars appear as one point of light to the naked eye, but through a telescope, the system reveals its complexity. The 2 brightest members are called Alpha Centauri A and Alpha Centauri B. They are both similar to our Sun, though not identical. Alpha Centauri A is slightly larger and brighter, a bit more massive, burning with a warm yellow glow. Alpha Centauri B is somewhat smaller and cooler, with a slightly orange tint. Together, they orbit each other in an elaborate dance that takes roughly 80 years to complete. Their orbit is not a simple circle. It is an ellipse, and the distance between the 2 stars changes as they move. At their closest approach, they come within about 11 astronomical units of each other, roughly the distance from our Sun to Saturn. At their farthest, they separate to about 35 astronomical units, beyond the orbit of Neptune. From the surface of a planet orbiting one of these stars, the companion sun would appear sometimes as a brilliant beacon, far brighter than any star in our sky, and at other times as a more distant, but still dazzling light. The 3rd member of the system is called Proxima Centauri. It is the closest of the 3 to us, and therefore the closest star to our Sun. Proxima lies at a distance of about 4.24 light-years, just slightly nearer than the A and B pair. But Proxima is not like its companions. It is a red dwarf, a small, cool star with only about 1/8 the mass of the Sun. It burns dim and red, emitting most of its light in infrared wavelengths our eyes cannot see. If you were standing on Earth and looked toward Alpha Centauri, you would not see Proxima at all without a telescope. It is far too faint. Proxima orbits the A and B pair at an enormous distance, perhaps 13,000 astronomical units away, more than 300 times farther than Neptune orbits our Sun. Its orbit takes hundreds of thousands of years to complete, perhaps even longer. Some astronomers have questioned whether Proxima is truly bound to the system or simply passing nearby. But current evidence suggests it is indeed a permanent member, tethered by gravity to its 2 brighter siblings. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. They called it Proxima b. It is roughly the same size as Earth, perhaps slightly larger, and it orbits its star at a distance of about 7.5 million kilometers. This is much closer than Earth orbits the Sun, but Proxima Centauri is much cooler and dimmer than the Sun, so the planet receives a similar amount of warmth. The orbital period is just over 11 days. A year on Proxima b lasts less than 2 weeks. The discovery sparked immediate interest. A potentially Earth-sized planet orbiting in the habitable zone of the nearest star to our own seemed almost too convenient. Could there be life there? Could the planet have liquid water? Could it support an atmosphere? The reality is more complicated. Red dwarfs like Proxima Centauri are unstable. They produce powerful flares, sudden eruptions of energy and radiation that sweep across any nearby planets. Proxima b, orbiting so close to its star, would be bathed in these flares regularly. The radiation would strip away any atmosphere unless the planet had a strong magnetic field to protect it. Even then, the surface might be scoured by high-energy particles. There is also the problem of tidal locking. Proxima b orbits so close to its star that the same side likely always faces the star, just as the same side of the Moon always faces Earth. One hemisphere would be locked in eternal day, baking under the red light of Proxima. The other hemisphere would be locked in eternal night, frozen in darkness. Any water or atmosphere would likely migrate to the cold side and freeze unless strong winds could circulate heat around the planet. These challenges do not mean Proxima b is lifeless. Life, if it exists there, would simply need to adapt to conditions very different from those on Earth. The planet remains a tantalizing target for future study, and astronomers continue to observe it, searching for signs of an atmosphere, hints of water, anything that might suggest habitability. The distance to Proxima Centauri, 4.24 light-years, translates to about 40 trillion kilometers. With current spacecraft technology, the journey would take tens of thousands of years. Voyager 1, traveling at 17 kilometers per second, would need more than 70,000 years to arrive, if it were aimed in the right direction. Even our fastest probes using gravitational slingshots and every available boost would take many human lifetimes to reach the system. There are concepts for faster travel. The Breakthrough Starshot initiative has proposed sending tiny probes equipped with light sails toward Alpha Centauri. Powerful lasers on Earth would push these sails, accelerating the probes to perhaps 20% of the speed of light. At that velocity, the journey would take roughly 20 years. The probes would be small, weighing only a few grams, carrying minimal instruments. They would fly past the system at incredible speed, snapping photographs and taking measurements before continuing into the void beyond. The data would take another 4 years to reach Earth, transmitted back as radio signals crawling across the light years. This remains theoretical. The technology does not yet exist. The lasers required would need to be extraordinarily powerful. The sails would need to be impossibly thin and light. The probes would need to survive the journey through interstellar space, enduring dust impacts at relativistic speeds. But the idea represents our best hope so far for reaching another star within a human lifetime. Alpha Centauri stands as both a promise and a reminder. It is our nearest neighbor, the closest we can get to another sun. And yet it remains unreachable, separated from us by a gulf so wide that even light takes years to cross it. But Alpha Centauri is not alone in our vicinity. Within a few dozen light years scattered through the darkness are many other stars. Within a sphere roughly 12 light years across, centered on our sun, there are only a handful of star systems. Most of them are invisible to the naked eye. Most of them are red dwarfs, small and cool, burning quietly in the darkness. If you were to look up at the night sky and try to spot these nearest neighbors, you would see only one or two. The rest hide in plain sight, too dim for unaided human vision. After Alpha Centauri, the next closest star is Barnard's star, located about 6 light-years away. It is another red dwarf, even smaller and dimmer than Proxima Centauri. Barnard's star holds the distinction of having the largest proper motion of any known star. Proper motion refers to how much a star appears to move across the sky over time, not because of parallax, but because of its actual movement through space relative to the Sun. Most stars appear fixed in their constellations, unchanging over human lifetimes. But Barnard's star moves noticeably. It shifts its position by about 10 arc-seconds every year. That may sound insignificant, but over the course of a few centuries it moves a distance equal to the width of the full moon. In roughly 10,000 years, it will have drifted across a substantial portion of the sky. This rapid motion tells us that Barnard's star is traveling quickly through our region of the galaxy, not orbiting the galactic center at quite the same speed or direction as the Sun. For a time, astronomers believed Barnard's star might host planets. Observations in the mid-20th century suggested wobbles in its motion, hints of gravitational tugs from unseen companions. Later analysis revealed these wobbles were likely errors in measurement. The star appeared to be alone. More recently, however, improved instruments have detected what may be a super-Earth planet, orbiting Barnard's star at a distance where temperatures would be extremely cold. The planet, if it exists, would be frozen and barren, far outside any habitable zone. Beyond Barnard's star, at distances between 7 and 10 light-years, lie several more red dwarfs. Wolf 359 sits about 7.9 light-years away. Lalande 21185 lies at just over 8 light-years. These stars are faint, unremarkable except for their proximity. They have been catalogued, measured, and observed, but they do not capture the imagination the way brighter, more dramatic stars might. They are simply there, small points of dim red light, closer to us than most stars, but still impossibly far. Red dwarfs are the most common type of star in the galaxy. They make up roughly 3/4 of all stars. They are small, with masses ranging from about 8% to 40% of the Sun's mass. They burn their hydrogen fuel slowly, far more efficiently than larger stars. A red dwarf can live for trillions of years, far longer than the current age of the universe. Some red dwarfs that formed in the early days of the cosmos are still in their youth, barely changed since their birth. They will continue shining long after stars like our Sun have exhausted their fuel and faded away. The dominance of red dwarfs in our neighborhood is not an accident. It reflects the nature of star formation itself. Small stars are easier to make. They require less material, less energy. Large, bright stars are rare because they demand vast amounts of matter to collapse into a dense enough core. When we look at the nearest stars, we are seeing a representative sample of the galaxy. Most stars are small. Most stars are dim. Our Sun, medium-sized and yellow, is actually more luminous than the majority of stars in existence. Not all nearby stars are red dwarfs, though. Sirius, the brightest star in our night sky, lies at a distance of about 8.6 light-years. It is close enough to appear brilliant, and it is intrinsically luminous, more than 20 times brighter than the Sun. Sirius is a binary system, consisting of Sirius A, a bright white main sequence star, and Sirius B, a white dwarf. White dwarfs are the remnants of stars that have exhausted their nuclear fuel. When a star like the Sun runs out of hydrogen to fuse, it swells into a red giant, then sheds its outer layers, leaving behind a hot, dense core. This core is the white dwarf. It no longer generates energy through fusion. It simply radiates away the heat it has left, gradually cooling over billions of years. Sirius B is about the size of Earth but contains nearly the mass of the Sun. A teaspoon of its material would weigh several tons. Sirius A and Sirius B orbit each other every 50 years, separated by a distance roughly equal to that between the Sun and Uranus. From Earth, Sirius appears as a single bright point, but through a telescope, the two stars can be distinguished, though Sirius B is faint compared to its blazing companion. The existence of Sirius B was predicted before it was ever seen. Astronomers noticed that Sirius A wobbled slightly in its path across the sky, suggesting the gravitational influence of an unseen companion. When telescopes improved, the companion was finally observed, confirming the prediction. It was one of the first white dwarfs ever discovered, and it helped astronomers understand what happens to stars when they die. Our local neighborhood, this small collection of stars within 10 or 12 light years, is quiet. There are no supergiants here, no brilliant blue stars, no violent stellar explosions. There are only small red dwarfs, a few sun-like stars, and the occasional white dwarf remnant. It is a calm, unassuming region of space. And yet, even here we find diversity. We find binary systems, planets, stellar corpses, and stars in every stage of their long lives. The Sun is not typical of its surroundings in one important respect. It is larger and brighter than most of the stars nearby. It stands out. If an astronomer from another star system were to survey this region, they might notice our Sun as one of the more luminous objects in the area, a relatively rare example of a yellow dwarf star. These stars, scattered across the nearby light years, form the immediate backdrop of our existence. They are our closest companions in the galaxy, and yet they remain distant, unreachable, separated from us by years of light travel and gulfs we cannot cross. But they are only the beginning. Beyond this small neighborhood, within a sphere of 50 or 100 light years, many more stars await. When we expand our view to include stars within 50 or 100 light years of the Sun, the sky begins to fill with familiar names. These are the stars we recognize, the ones that form the constellations, the ones ancient civilizations wove into their myths. Many of them are bright enough to be seen easily from Earth, and some are among the most prominent lights in the night sky. Vega sits about 25 light-years away in the constellation Lyra. It is a blue-white star, young and hot, burning with roughly 40 times the luminosity of the Sun. Vega is one of the brightest stars visible from the northern hemisphere, and it has been studied intensely for centuries. Astronomers discovered a disk of dust surrounding Vega, the remnants of planetary formation. This disk suggests that planets may orbit the star, though none have been confirmed yet. Vega rotates rapidly, spinning so fast that it bulges at its equator, making it wider than it is tall. Arcturus lies about 37 light-years away in the constellation Bootes. It is an orange giant, a star that has exhausted the hydrogen in its core and expanded into a much larger, cooler form. Arcturus is moving through our region of the galaxy at high speed, following an unusual orbit that suggests it may have originated in a different part of the Milky Way. It is one of the brightest stars in the sky, easily visible even from urban areas. Altair in the constellation Aquila is only about 17 light-years away. Like Vega, it is a bright, white star that rotates very quickly. It completes a full rotation in less than 10 hours, compared to the Sun's rotation period of about 25 days. This rapid spin distorts its shape, flattening it at the poles and stretching it at the equator. Altair is close enough and large enough that astronomers have been able to measure this distortion directly, making it one of the few stars for which such detailed observations are possible. Fomalhaut, about 25 light-years away in the constellation Piscis Austrinus, is another bright, young star surrounded by a disk of dust and debris. In 2008, astronomers announced the discovery of a planet orbiting Fomalhaut, visible in images taken by the Hubble Space Telescope. The planet, called Fomalhaut B, appeared to be moving through the debris disk, clearing a path as it orbited. Later observations have cast doubt on this interpretation. The object may not be a planet at all, but rather a dispersing cloud of dust from a collision between smaller bodies. The mystery remains unsolved. These stars and many others within this range represent a broad diversity of stellar types. Astronomers classify stars based on their surface temperature, which correlates with their color. The classification system uses the letters O, B, A, F, G, K, and M, progressing from the hottest, bluest stars to the coolest, reddest ones. O-type stars are rare, massive, and short-lived. B-type stars are also hot and blue, though less extreme. A-type stars like Vega are white and bright. F-type stars are slightly cooler, yellowish-white. G-type stars like our Sun are yellow. K-type stars are orange, cooler still. M-type stars are the red dwarfs, the smallest and most common. Our Sun is a G-type star, sitting comfortably in the middle of the sequence. It is neither the hottest nor the coolest, neither the largest nor the smallest. It is in many ways unremarkable. But this ordinariness may be important. Extreme stars, the massive blue giants and the tiny red dwarfs, present challenges for life. Blue giants burn out quickly, living only a few million years before exploding as supernovae. They do not provide the stable, long-term conditions that life might need to develop. Red dwarfs, on the other hand, are prone to violent flares and tend to tidally lock their planets, creating harsh, uneven environments. Yellow stars like the Sun, and to some extent orange K-type stars, offer a middle ground. They burn steadily for billions of years. They are calm, predictable. Planets in their habitable zones receive consistent warmth without the danger of sudden, lethal radiation bursts. This may be why the search for life often focuses on stars similar to the Sun. Within our extended neighborhood, several Sun-like stars have become targets of interest. Epsilon Eridani, located about 10.5 light-years away, is a K-type star slightly cooler and smaller than the Sun. It is young, perhaps less than 1 billion years old, and it has a confirmed debris disk. At least one planet, a gas giant several times the mass of Jupiter, orbits Epsilon Eridani at a distance of roughly 3 astronomical units. The system is still forming, still settling. Dust and small bodies continue to collide and coalesce. It may resemble our own solar system as it was billions of years ago. Tau Ceti, about 12 light-years away, is another Sun-like star. A G-type only slightly smaller and dimmer than our Sun. For decades, it has been considered a prime candidate for searches for extraterrestrial intelligence. Radio telescopes have pointed toward Tau Ceti, listening for signals, for any hint of artificial transmission. None have been detected. but the star is known to host at least 4, possibly 5 planets, some of which may lie within or near the habitable zone. These planets orbit closer to their star than Earth does to the Sun, but because Tau Ceti is slightly cooler, the temperatures might still allow for liquid water. The discovery of planets around nearby stars has transformed our understanding of the galaxy. We now know that planets are common, perhaps even ubiquitous. Nearly every star likely hosts at least one planet, and many host several. Within 100 light-years of the Sun, there are thousands of stars and therefore likely thousands of planetary systems. Some of these planets are gas giants like Jupiter. Others are rocky like Earth. Some orbit in the habitable zone where temperatures allow for liquid water. Others are frozen, scorched, or battered by radiation. We have not visited any of these worlds. We have not seen them up close. But we have detected them, measured their sizes and orbits, and begun to characterize their atmospheres. Future telescopes may allow us to search for biosignatures, chemical traces of life, in the atmospheres of the nearest exoplanets. We may one day know whether we are alone or whether life exists on worlds orbiting nearby stars. The stars within 50 or 100 light-years form the fabric of our immediate galactic surroundings. They are varied, numerous, and intriguing. But even here, among the bright and familiar, the distances remain staggering. And between these stars lies something equally profound. The space between stars is not merely empty. It is profoundly, almost incomprehensibly empty. When we talk about interstellar space, we are talking about a void so complete that it challenges our ability to grasp what emptiness truly means. Consider the scale. If you were to shrink the Sun down to the size of a marble, about 1 centimeter across, the nearest star would be more than 300 kilometers away. Imagine placing a marble on the ground in one city, then traveling to another city hundreds of kilometers distant and placing a second marble there. The space between those 2 marbles, scaled appropriately, represents the gulf between our Sun and Alpha Centauri. Everything in between is empty. In our region of the galaxy, stars are separated by an average of about 4 to 5 light-years. This is typical for the galactic disk, the flat plane where most stars reside. In some denser regions near the galactic center, stars may be closer together. In the sparse regions of the galactic halo, they may be farther apart. But nowhere in the galaxy are stars truly close to one another, not in any sense we would recognize. This emptiness is not absolute. Interstellar space does contain matter, but the density of that matter is almost negligible. The interstellar medium, as astronomers call it, consists primarily of hydrogen and helium gas, along with trace amounts of heavier elements and dust grains. The density of this gas averages about 1 atom per cubic centimeter in the regions near the Sun. In some areas, particularly in vast clouds of gas and dust, the density can climb to hundreds or even thousands of atoms per cubic centimeter. In other regions, especially in the hot, tenuous bubbles blown out by supernova, the density can drop to 1/100th of an atom per cubic centimeter. To put this in perspective, the air you breathe contains roughly 30 million trillion molecules per cubic centimeter. The interstellar medium is thinner than the air by a factor of trillions upon trillions. It is a vacuum far better than anything we can create in a laboratory on Earth. Our best vacuum chambers can reduce the density to perhaps 1 million molecules per cubic centimeter. Interstellar space is 1 million times emptier still. If you were to travel through interstellar space in a spacecraft, you would encounter almost nothing. Hours might pass between collisions with individual atoms. You would drift through a darkness broken only by the distant light of stars, with no landmarks, no points of reference, nothing to indicate your position except the slow shift of star patterns over months and years. Yet this near vacuum is not completely featureless. Magnetic fields thread through interstellar space, weak but extensive, shaping the flow of charged particles. Cosmic rays, high-energy particles, accelerated by supernovae and other violent events, streak through the void at nearly the speed of light. Occasionally, you might pass through a wisp of dust, grains of carbon or silicate no larger than particles of smoke, remnants of long-dead stars expelled into space. In certain regions, the interstellar medium becomes denser and more visible. Nebulae, vast clouds of gas and dust, can be seen from Earth as glowing or dark patches against the background stars. Some nebulae shine because they are illuminated by nearby stars, their gas excited by ultraviolet light. Others are dark, blocking the light of stars behind them, appearing as voids in the star field. These clouds are the birthplaces of stars, regions where gas collapses under its own gravity, eventually igniting nuclear fusion and forming new suns. But between these clouds, in the ordinary interstellar medium, there is little to see and little to encounter. The emptiness dominates. A journey through interstellar space would be a journey through near nothingness, a passage through a void so vast and so empty that the mind struggles to accept it. This emptiness has profound implications for interstellar travel. Any spacecraft venturing between stars would travel alone, cut off from everything, surrounded by a darkness that extends in all directions for light years. There would be no fuel stations, no resources to harvest, no places to stop. The ship would need to carry everything it requires for the entire journey, or find ways to generate what it needs from the sparse material it encounters. The isolation would be total. Communication with Earth would become increasingly delayed as the distance grew. A message sent from a spacecraft 1 light-year away would take 1 year to reach home, and the reply would take another year to return. A conversation would be impossible. Instructions, questions, updates, all would be separated by years of silence. The crew, if there were a crew, would be on their own, making decisions without guidance, traveling through a void where help could never arrive in time to matter. Even the stars themselves would offer little comfort. From within interstellar space, midway between 2 stars, both suns would appear as mere points of light, no brighter than the other stars scattered across the sky. The sun, viewed from a distance of 2 light years, would be just another star, indistinguishable from the thousands of others visible. There would be no sense of home, no visual connection to the place left behind. The emptiness of interstellar space is one of the fundamental features of the galaxy. It is not an obstacle that technology can overcome by building better engines or faster ships. It is simply the nature of the cosmos. Stars are rare objects, separated by enormous distances, isolated from one another by voids that nothing can cross quickly. This isolation defines our existence. We live on a world orbiting one of these isolated stars, surrounded by light years of near nothingness in every direction. Our nearest neighbors are unreachable. The stars we see in the sky are beyond our grasp, not because we lack the will or the ingenuity to reach them, but because the universe is built on a scale that dwarfs our capabilities. And yet, we have found ways to bridge these distances, not with spacecraft, but with knowledge, with observation, with understanding. We have measured the emptiness, mapped it, come to know its properties and its extent. We have reached across the light years with our instruments and our minds, even if our bodies cannot follow. The distances to the stars are, by any human measure, insurmountable. We have sent spacecraft to the moon, to Mars, to the outer reaches of the solar system. We have landed rovers on distant worlds and flown probes past the orbits of Neptune and Pluto. But the gap between the edge of our solar system and the nearest star is so vast that it renders all of these achievements almost trivial by comparison. There's a strange contradiction in our relationship with the stars. We can see them. We observe them every night, cataloguing their positions, measuring their light, analyzing their spectra. We know their temperatures, their masses, their compositions. We have discovered planets orbiting them. We understand, in remarkable detail, what they are and how they work. And yet we cannot reach them. We cannot visit them. We cannot send even a single probe to arrive within a human lifetime. This contradiction defines our cosmic situation. We are observers, not travelers. We are bound to our star, to our small patch of space, unable to cross the gulfs that separate us from our neighbors. The universe has given us eyes to see across light years and minds to comprehend what we see, but it has not given us the means to go there. When we look at Alpha Centauri, the light entering our eyes left that star more than 4 years ago. We are not seeing Alpha Centauri as it is now. We are seeing it as it was, frozen in the past. If something dramatic were to happen to that star, if it were to flare or dim or somehow change, we would not know for more than 4 years. The stars we observe are echoes, images carried across the void by light that has traveled for years, decades, centuries. This delay is not unique to Alpha Centauri. Every star we see is displaced in time. Sirius, 8.5 light years away, appears to us as it was 8.5 years ago. Vega, 25 light years distant, shines with light that left its surface a quarter of a century in the past. The farther we look, the deeper into the past we see. The stars form a map not just of space, but of time, each one a window into a moment that has already passed. In a sense, we are surrounded by ghosts. The stars we see may no longer exist in the forms we observe. Some may have changed. Some, though this is unlikely on human timescales, may have died. We would not know. The light continues to arrive, faithful and unchanging, even if its source has transformed. Humanity has imagined many ways to reach the stars. Generation ships, vast vessels that would travel for centuries, their passengers living and dying aboard, their descendants eventually arriving at distant worlds. Suspended animation, freezing travelers in time so that the journey passes in an instant for them, even if decades elapse outside. Breakthrough propulsion systems, fusion drives, antimatter engines, solar sails pushed by lasers, technologies that remain theoretical, dreams of what might be possible if we solve the fundamental problems of energy and engineering. None of these solutions are easy. Most are far beyond our current capabilities, but they are not necessarily impossible. Humanity has surprised itself before, achieving what once seemed unthinkable. We have walked on the moon. We have split the atom. We have decoded the structure of life itself. Perhaps in time we will find a way to cross interstellar space. For now, we reach the stars in other ways. Our radio signals, traveling at the speed of light, have been radiating outward from Earth since we first began broadcasting in the early 20th century. These signals form an expanding sphere, growing larger every year, carrying the sounds and images of human civilization into the cosmos. The nearest stars have already been touched by this sphere. Our earliest radio transmissions from a century ago have passed Alpha Centauri and continue onward. Dozens of stars now lie within this bubble of human-generated signals, silent witnesses to our existence. Whether anyone or anything is listening, we do not know. The universe may be full of life, or we may be alone. Either possibility is profound, either would change how we understand our place in the cosmos. There is another way in which we have already reached the stars, a way more fundamental than radio signals or spacecraft. We are made of star material. The atoms in your body, the carbon, oxygen, nitrogen, and all the heavier elements were forged in the cores of stars that lived and died before the sun was born. Those stars exploded as supernovae, scattering their contents across space, seeding the clouds from which new stars and planets would form. Our world and everything on it is built from the ashes of those ancient suns. We are not separate from the stars. We are part of them. We carry their legacy in every cell. In this sense, we are already travelers, already participants in the vast cycles of the cosmos. The journey is not one we can take in ships. It is one that has already happened over billions of years through the death and rebirth of stars, the formation of planets, the emergence of life. We are the stars looking back at themselves, wondering about their origins. Perhaps this is enough. Perhaps the purpose of consciousness, of intelligence, is not to conquer the distances between stars, but to observe them, to understand them, to appreciate the beauty and scale of what exists. We may never walk on the surfaces of worlds orbiting Alpha Centauri or Barnard's star, or any of the thousands of stars within reach of our telescopes. But we have touched them with our minds. We have measured them, named them, unraveled their secrets. We have brought them into human understanding. The stars remain distant. They remain unreachable, at least for now. But they are not unknown. We have closed the gap between ourselves and the cosmos, not with speed, but with knowledge. And in doing so, we have discovered something unexpected. The universe is not cold or indifferent. It is home. It is where we came from, and it is where we remain, connected by light, by gravity, by the slow turning of the galaxy. When you look up tonight and see the stars, remember that you are looking across both space and time. The light has traveled for years to reach you. The distances are beyond comprehension, but the connection is real. You are part of this. You are made of stars. And the stars, distant as they are not so far away after all.